Welcome, everyone. So I'm Aurelian, one of the co-organizers of this Flow seminar. I know Peter Richterig, Virginia Smith, Dan Alistar, and Samuel Orbat. So I'm going to be hosting the talk today. So just for newcomers, the goal of this seminar is to provide a forum to discuss the latest scientific results in all aspects of federated learning. So we try to cover many aspects like distributed optimization, learning algorithms, privacy, crypto, things related to personalization or communication compression, and also aspects related to systems, hardware, and of course also applications. So just to remind also how this is going to work. So before I introduce today's speaker, you're welcome to ask questions during the talk. So all mics are off by default for audience members, but you can use the raise hand feature in the participants menu, or you can write the question in the chat, and then Samuel and I can ask the question for you, or we can turn on your mic so you can ask the question yourself. Okay, so feel free to ask questions during the talk. There will also be time at the end, of course, to ask more questions. Right, so our speaker today is Richard Nock. Thanks a lot for accepting our invite. So Richard is a research scientist at Google Brain and also an honorary professor at the Australian National University. Prior to that, he was affiliated with Data61 and NICTA, also in Australia. So Richard has worked on many things in machine learning and information theory, with contributions, for instance, in the theory of boosting, the use of various divergences in machine learning algorithms, like for clustering, for instance, and also in theory of machine learning, like to define appropriate loss functions and surrogates. And in recent years, he has also worked quite a lot on privacy and federated learning. And so today he will talk about probably a bit underexplored setting of federated learning, which is this vertically partitioned data, where multiple data providers hold different features about common data points. And in this context, you have to link the observations of the different data sets together, and this might be prone to errors. And so I think Richard will show us how to analyze and control the impact of such record linkage errors on the downstream performance of the machine learning model that you learned. Richard, it's up to you. Thanks a lot for accepting to give this talk.
Thank you very much, Aurélien and Samuel and everybody for inviting me. That's a pleasure actually to present this work, which was done in NICTA and Data61, as you said, with a team of great people. So essentially back then, most of these people actually were, including me, were affiliated with Data61. So the work that I'm going to present is the work of this team. Don't hesitate to ask questions during the presentation if you have. My chat window is open, so I can see your questions if you type them or just ask. That's as simple as well. So today we're going to talk about as Aurélien said, the impact of record linkage on learning from feature partition data. So let's have a very brief summary statement about, let's say, the key features relevant to federated learning. There is, of course, a learning component, a distributed component, a privacy component. Yet in this talk, we are going to stand essentially in between, let's say, the learning and the distributed features of federated learning. I'm not going to talk about privacy, even when there will be some, I suppose, obvious connections with some privacy context during this talk. So don't hesitate to ask questions related to privacy if you have some. It was also the purpose of this team, which was by the way named Confidential Computing. So it was also the purpose of this team to explore the privacy content of the research we were doing. So let's first start with a very simple statement of what is the, let's say, the problem in the simple case of all the data sitting in one place. So this is just, let's say, batch centralized learning. So that's a supervised learning problem, which means the input that we have is a set of examples, each of which consists of an observation and a class. So you can suppose that the observations are split between features coming from a medical domain, features coming from a pharmaceutical domain, n plus p. And what we want is essentially a model that's going to predict the class C from n plus p together. We are going to restrict this talk to linear models. And we are going to learn this model by minimizing a loss function. And again, that's very important. In this case, there's a single peer, a single location, a single database, which holds all the data. So essentially, if we have a look at classical tools from learning theory, well, they are going to tell us that with a high probability, somehow what we're going to learn on our database is going to be a more or less good representation of what will happen on the whole population. And the more or less good is up to some additional penalty parameters that are here noted: capacity and rate. The key point about this talk is that essentially the capacity parameter is going to depend on the model class that we have chosen, and some data features as well, such as the size. The rate is more dependent on the loss and on some data features as well, such as the size. And so the message, if I can summarize a big problem into a simple statement, is the larger, the bigger, the more data that we have, somehow the more confident we are that what we are going to obtain on training is going to be good on testing as well. So for that reason, if we switch very rapidly to the distributed model where we have this time two peers, each of them handling subsets of the population on the same set of features. So this is a setting called horizontal partition. Then actually we immediately understand the reason why it's actually good to learn from the complete set of data, because with two peers, we get more data than with just one. So more data, again, better models, more confidence into the models that we build. So there's barely anything to add to the picture of, let's say, machine learning to understand why it's beneficial. But if the data is vertically partitioned, maybe it's a little bit more unclear, because in this case, we have the two peers handling essentially information about the same population, except that the difference in this case is that peers have features that the other doesn't have. So essentially, by joining the two data sets, we have more features. Not more examples, but more features. So it seems reasonable and intuitive that somehow we could obtain better models, but how and why, that's actually a question. And that's one of the purposes of this talk, to actually present some way to understand better this relationship. So let's cast ourselves now into this vertical partition model, in which, say, from our n plus p data, which was held by a simple single database, we now have two peers. One of the peers handles the medical data, the other one gets the pharma data. We assume that one of the peers, maybe both, have the class information. Our goal is essentially the same. So we want to train a classifier which is going to rely on the complete set of features to predict the class. So if we look a little bit closer, before learning our classifier, we need somehow to build examples. And this involves a step which is called record linkage, sometimes entity resolution. You have many other different names. So record linkage, RL, here is just a way to link the two data sets and figure out who is who among the data. So the point is, just give me 1 second. Okay, I hope you still can see my slides. Okay, so the point is, if in the real world we had, let's say, unique identifiers to uniquely design individual, if these unique identifiers, these UIDs, were noise-free, then there would be no problem, essentially. We would just have to reconstruct the whole database using these perfect UIDs. We will get the complete batch data. Of course, there would be some privacy concerns, but again, that's not the purpose of this talk. And then we would just need to learn this model, theta star, and we would just be as happy as in the horizontal partition case. The problem is that, oops, okay. I'm sorry, I have a little problem. Okay. Right, that's much better. The problem is that UIDs are noisy in the real world. So we have no way to exactly match the people in between the databases, we make mistakes. So for that reason, we can model the mistakes that we make in between the two databases, given that, again, they actually point to the same population. So we can model the mistakes using a simple permutation matrix, which is going to give us the way, essentially, we should change our linkage to actually get to the ideal record linkage. Of course, we don't know p-hat. But the point is, if we were able to actually have a good approximation, or if not the right one, we would be able to learn the true classifier. So that would be the perfect classifier that we would have in the centralized version. Otherwise, we just have an approximation of p-hat, and then we learn another classifier, of course, which I name theta tilde star. And so the question is, how does theta tilde star relate to theta star? So here is the problem. The problem is that which is not really a problem when you think about it. Record linkage literally lives in the land of plenty. There are plenty solutions to carry out record linkage or entity resolution between data sets. So you have here a pointer to a recent survey in arXiv, which contains pointers to more than 200 references. And as a comparison, this is about 3 times more than a recent survey, same journal, same format on differential privacy. So that gives you an idea of the scale of the landscape. But the point is that there is, and that's a big difference, for example, with differential privacy, there is little formal understanding on, even to start with, record linkage, and even less so, of course, how it somehow impacts machine learning. So our approach is going to be the following one. The thing we would like to do, the objective that we had at the beginning, was to quantify a discrepancy. Since they are linear separators, linear classifiers, that we learn, actually it's very easy to compute. But we would like to bound this discrepancy as a function of the data that we have, this unknown permutation matrix p-hat, and maybe additional parameters. Always remember that these classifiers here, theta star and theta tilde stars, are optimal models on training data. I'm not going to talk about generalization in this seminar. The difference between the two is that our model, theta tilde star, is learned from an approximate version of record linkage, the ideal record linkage, which, if it were known, would give us directly theta star. So what is the discrepancy? So let's have a look first at the key parameters that are important to quantify this discrepancy. And let's first have a look at the permutation matrix p-hat. So there are 3 key parameters that we need from p-hat. So let's backtrack a little bit. So we have our training.
Can I just ask a very quick question? So just to understand this p-hat is if you have your noisy record linkage and you multiply by p-hat, you get the correct linkage. Is that roughly what that matrix is? Okay.
Yes. So that's the complete information that you need somehow to correct your mistakes to get theta star at the end of of training.
Okay, so if this matrix is, say, the identity, it means in fact your linkage was completely correct.
You can formalize the problem like this. Yes, indeed.
Okay.
Of course, not forgetting that in fact you don't know somehow the ideal correspondence. So this identity looks like it's an easy way to go forward, but it's in fact harder than just let's say starting with this idea of the optimal permutation. But otherwise, you're absolutely right.
Okay.
So here are the key parameters that we need. So we have our training sample that we have learned after noisy record linkage. So we have observation, so the x hat, because it's noisy, and the classes, the y, so there is no real issue for the classes. So you have in the middle of the slide, essentially the data set, the observations of the data as we have them. Of course, we somehow don't observe the colors in this case. You have the unknown perfect record linkage that's also depicted in here. Again, we don't observe the colors. So we end up with something that's somehow a mix of the ideal data matrix, and we have no idea essentially who is in fact who. But the point is And that's one of the first key parameters that we need. This permutation, p hat, can be reconstructed as a product of elementary permutations. So each permutation can be reconstructed as a product of permutations, each of which actually affects exactly 2 observations, right? And essentially changes one part, let's say the B part. We somehow anchor the A part into a reference. So this permutation just changes the B parts among the observations, right? So you have one example here. T, the size of this permutation is 1 parameter. There's another parameter, because each elementary permutation affects, in fact, at most 4 observations from X. So if you have a look in this case at the part of the observations which is affected in A, you have 2 in this case, the yellow and the red one. And in B, you have 2 as well, the green and the blue one. So you have 4 observations that are, in fact, affected somehow by this permutation, or that can be used to define essentially what are the changes made by this permutation. So let's just assume that somehow, if we made this mistake during record linkage, it's because the observations involved are not too dissimilar from each other. So you have, let's give them names, A and B. So that's the observation whose A part is involved. A prime, B prime, that's the observations whose B part is involved. More specifically, because it's not the whole observations that are in fact involved in PT, we are going to assume that the part of the observations which is relevant to P is in fact not too dissimilar from each other. So we have the part of A, the part of B, which comes from A, which is not too dissimilar, and same story from A prime and B prime. So more specifically, we're going to say that PT is epsilon tau inexact, if and only if, well, if we were to compute the inner product of any of these subvectors with the corresponding subvector of a vector W, then this would be bounded. So essentially, again, that's the key part, we don't make lots of mistakes among the observations. And so you have these inequalities that are essentially defined by these parameters epsilon and tau. I will come back later on the what we do from with these parameters. But the point is, I will say that p hat itself is epsilon tau inexact if each of the elementary permutation is epsilon tau inexact. So we don't use epsilon tau as they are, but we are going to aggregate them in a single parameter, which is called psi. So psi is essentially just a sum of the 2 parameters properly normalized to make sure that we don't mix pears and apples. So we're just going to sum epsilon plus tau divided by the maximum norm in our data set. And the point is, this psi, which is the minimum over these quantities, is never too big. In fact, it's always smaller than 2. But let's remember psi as somehow an inaccuracy among observations that we are making throughout these permutations. The last parameters actually cares about the class, because it may be the case as well that somehow we mix observations having different classes. So in this case, because we assume that PA has the classes, where we are just going to count the number of times actually the 2 observations involved in PT from A have a different class. We normalize it by the size of T. So we get a proportion rho, and this is going to complete all our key parameters that we need. So to remember, we have these 3 key parameters. One is T, the number of mismatches somehow that we make throughout P. The second one is psi, the mismatches among observations. And the first one, rho, is the mismatches among the classes. So then we, of course, need to assume that somehow we have a loss function that we use to learn our model. So we will just make the assumption that the function that we minimize is what we call a ridge regularized Taylor loss. So Taylor losses have a long-standing history in the field of crypto plus machine learning, let's just say it this way, because they are very simple approximation of eventually more complex losses. So we just have one of these losses with these 3 parameters N, B, and C satisfying some very loose constraints. Obviously, there would be some good choice for learning and others that would be not as good as, but I won't care too much about this. And then we have this ridge regularizer, which involves a symmetric positive definite matrix gamma. So that's it for the essentially the learning component. So the learning component is just the design of a loss and the choice of a loss, which is just, let's say, a quadratic loss, ridge regularized. So we are going to make an assumption which we call the data loss assumption. Essentially, it's split in two. The first part is that the loss that we're considering is in fact sufficiently regularized. So you have this condition which involves statistics about the data, more precisely the maximum square norm and the average square norm. And you have this other part which involves the minimal eigenvalue of gamma. So we have this condition which in fact states that indeed we have, let's say, sufficient regularization of the loss that we use. The second condition is just that we have enough data. So if you have a closer look at the right-hand side of this inequality involving m, then it's just stating that m is larger than a constant. Remember that psi is never larger than 2. So let's have a look at the results that we get. First result. So assuming that the data loss calibration holds, so again, enough regularization of our loss, enough data, then we get this upper bound, which is the sort of upper bound that we wanted at the beginning, because it involves on the left-hand side this discrepancy between theta star and our classifier, theta tilde star. So on the right-hand side, you have these various parameters, many of which actually relate to p hat. And you have these two additional delta parameters on the right-hand side. So the first one, delta theta, is a parameter which depends on the optimal classifier theta star. So essentially, the larger, the better. You can think of it as some sort of margin on the optimal classifier. The other one focuses more or is more related to properties of p hat. So you have the expression. So you can see that actually in this parameter, you have rho, so the error on classes which appears, and you have this function of psi, which I have plotted. So the plot is just here because the expression is a little bit more complicated. The plot is just here to tell you that, in fact, given that psi is always in between 0 and 2, L psi is, in fact, always smaller than 0.5. So it's never big. And of course, the smaller this delta parameter, the better it is for the bound. So let's now have a, let's say, maybe a simpler look at this inequality. Let's make this additional assumption that somehow p hat is small enough, which is called this alpha boundedness condition, which says essentially that t, the size of p hat, is bounded by a function of m and psi, the inaccuracy on the observations. And you have this parameter alpha in exponents. The first thing to have a look at is to realize that as this inaccuracy parameter psi in fact decreases, the bound in fact gets loose on t, right? So t can be alpha bounded for in fact larger values of alpha, and that's going to be important. Otherwise, in general, you can just think that somehow this holds if t is in fact negligible against square root m. So which means t needs to be quite small, in fact, for this assumption to hold. But the point is, if it holds, then we have this simplification of our theorem. So what you have here is a product of two quantities. So the one on the right-hand side is something that looks like what we had before. And you have this C of m parameter, which is in fact key in this case, because if you think machine learning, then what this parameter tells you is that the right-hand side, in fact, converges at a rate which is 1 over m to the power alpha. So essentially, that's the usual, let's say, ML picture in which the larger the number of examples that we have, the larger the data, somehow the better the bound is. So that's, let's say, an usual machine learning way to understand this bound.
Richard, maybe quick question on that. So
yes.
Okay, yeah, but okay, these things are. I was, I guess, surprised a bit that you could have 1 over m, but we are not looking at generalization here, like you said, right? So it's Absolutely. Not like it's fast rates or something
yes.
like that.
Yes. So okay, this is always remember these are guarantees on training. I'm not talking about generalization in this case. So because this is really about pinpointing somehow the effect of record linkage on training the model afterwards.
Right.
So disregarding all the additional consideration and issues that we might have in generalization.
Yeah, which you can just get by a triangle inequality in a way, right?
That's actually correct.
By having results on theta star. So
yes, that's correct. So to make this condition a little bit more concrete, let's have a look at a picture. So in this picture, as a function of m, so again, the size of the data set, remember vertical partition. So that's essentially the number of individuals that each database has. So you have here plotted the limit value of t, under which we have a guarantee in terms of alpha, right? So the bigger alpha, the better it is. So you have essentially two different conclusions from this picture. One, so considering again record linkage in record linkage plus machine learning pipeline, if you know that you're not going to make a big number of mistakes, so you have numbers on this picture, then essentially you can just be happy. Because somehow the approximation that you get in between theta tilde star and theta star just depends on C, and it converges. So again, the rate 1 over m to the power alpha depends on alpha, but that's anyway something that always goes to 0 as m increases. So that's just, let's say, a classical conventional picture. Otherwise, so if you have more mistakes than that, then it's probably a good idea to have a look at psi and rho, right? To somehow try either to select your record linkage algorithm or maybe design it in such a way that you're as well going to control these two parameters. But given this picture, which tells us somehow a message that has a very usual flavor in machine learning, let's have a quick backtrack on the problem that we're addressing. So somehow, again, this is vertical partition for machine learning, right? So again, let's make a quick summary. If the data is horizontally partitioned, federated learning is good because we have improved confidence in what to optimize, we have more examples, less uncertainty, better models. That makes sense. If the data is vertically partitioned, we get more features. So eventually we can assume that as m grows, that's the usual story. It's going to get better. But let's just consider that m is fixed. But we get more features. By getting more features, we have this intuition that somehow we should have a better theta star model. And if all this makes sense, so the vertical partition plus machine learning framework, then we should as well get a better theta tilde star, taking into account, of course, the eventual mistakes that a record linkage might do. How could we formalize this? Well, there is a simple way to think about this problem, which is to exploit the notion of margins. So a margin of a classifier theta here on example xy is just the product of the class times the classification of the example. So essentially, if it's positive, the example receives the right class. And the bigger this margin in absolute value, somehow the more confident is the classifier. So let's define what we call margin immunity. Let's say that theta tilde star is immune to record linkage at some margin, kappa, strictly positive. If for any example, it happens that we have the following condition. If we have, so to make a long story short, if this example has a large margin on theta star, then it's going to receive the right classification on theta tilde star. There's obviously a degradation of the, let's say, of the guarantees that we need to take into account because of record linkage, and it's quite obvious in this case, but let's just be happy with the fact that we want to predict the right label. So then if we can have this condition, if we can observe this, if we can prove this, then we have a way to somehow link the fact that vertical partition brings more feature and the fact that we should get better models. Because better features might just create models with optimal models. That's actually important, with larger margins, right? So somehow we would get the distribution of margins somehow moving to larger values, if within quotes. And therefore, we might get, if it does work indeed on theta tilde star, we might get smaller errors or larger accuracies. So the point is we do have a theorem of this exact flavor. So if the theorem says still, if we have this data loss calibration assumption, then theta tilde star is immune to record linkage as any margin kappa for which you have this condition. So what's interesting, I mean, this is kind of a machine learning bias to formulate this condition this way. You would maybe you would put kappa on the left-hand side, but let's just have a look at this inequality as is. So it tells you essentially that if p hat is good enough, which means if psi is small enough, it's t is small enough, if we have enough examples, then we are going to get immunity at smaller and smaller and smaller margins. And that's the key point, because in this case, we are going to get predictions that are going to progressively match the predictions of the ideal model learned after perfect record linkage. And this is what we would like to do precisely. If we add the condition that p hat is alpha bounded, then we have somehow a simpler condition, which I have stated with just m on the left-hand side. So again, in this case, if we have enough examples, that's kind of a usual picture again, then we can get margin immunity for smaller values of kappa. So now let's have a look at some experiments to somehow validate all this. So one very important thing is that we have done simulated experiments, only simulated experiments in this study from UCI domains. We did that because we wanted to actually be able to compute theta star and make comparisons. So what we have done is we have split vertically each UCI domain in two sets of features, one for each peer. We have for each domain some shared features, which makes a lot of sense because in the real world, you would have in many different cases, the peers actually knowing some joint features, for example, the birth date of their clients, the postal code, where they live, and so on. We have eventually noisified these shared features, but we have noisified them using some noise models that are, in fact, standard in record linkage. So these noise models actually take into account the human noise somehow. For example, you have a field which is textual. You make a mistake. In general, the character that's going to be missing is going to be a character that's close to the true one on your keyboard, right? If the true value is an age, for example, of a person, you are rarely going to miss an age of, let's say, 5 for an age of 80, but maybe more frequently miss the age of 5 for an age of 6. So you're going to more frequently, in fact, have closer values than values that are very distant from the actual one. So we have used as a baseline a very conventional greedy record linkage algorithm, which is fast. Plus, it brings actually a very nice guarantee. It has actually guaranteed approximation ratio with respect to the optimum, 0.5, which is quite good, given the simplicity of the algorithm. And we have tested two variations somehow. One variation in which the two peers A and B actually know the classes, and we noisify the classes in one of the peers, which is also a setting which you would encounter in practice because businesses collaborating would collaborate to predict a specific class, which they would at least partially know, each of them. So we suppose that A and B know the classes. We add eventually some noise in one of the peers. And then what we do is very simple. We do record linkage within the classes first, and then within the remaining linkage that need to be done. And the last case is essentially where one of the peers doesn't have classes. So what we do in this case is that the peer actually learns the classes via a partial greedy matching using only, let's say, the highest similarities in the record linkage, then learns the rest of the classes using these partial classes, and then we just repeat step one. So let's have a look at the observations. And first observation, margin immunity. So here is a data set from UCI, one white. On this plot, so don't look at the green curve yet. Just have a look at the red histogram. This histogram actually gives a histogram of optimal margin. So these are the optimal margin on theta star. Remember, we can compute theta star because we simulate the domains. So essentially, these margins for wine white are in between -2 and 3. This theta star model can actually make mistakes, of course, so you can have negative margins. Then what we do is we compute the cumulated error of our model, theta tilde star, as a function of where we are in these buckets, right? So essentially, we are going to pick a value of the optimal margin, and we are going to compute the relative error that we make on margins that are at least of this value. So this explains why if you consider very large margins, you're going to have a low error. And if on the other hand, you actually converge to the minimal margin, this is where, of course, we'll make all our mistakes. Hence, actually, the curve converges to 1. Remember, this is relative to the set of errors that we make. So this is not the actual error of theta tilde star. So then in between, we have a curve. And this is the curve that is actually interesting. Because it tells us in this case, which is quite nice, that, for example, we have 20% errors, at least, in fact, less than 20% errors happening on examples with strictly positive optimal margins. So that's one fact. But the more interesting fact is here, in fact. If you look carefully at the curve, you realize that there is, in fact, no error of theta tilde star, or almost no errors, on examples with optimal margin exceeding 0.5. And that's very interesting because the maximum margin is, in fact, close to 3. So it means that experimentally, we observe this margin immunity, and in fact, for quite small, strictly positive, of course, but quite small margins. So that's interesting. And the last experiment I'm going to talk about is somehow trying to get up to get a dial for record linkage and machine learning, somehow something that could signal that, record linkage is getting bad for machine learning. So to test this sort of high level, let's say, objective, we have crafted gradually harder record linkage problems. So what we have done is just putting more noise, either in the shared features or in the class. Remember the algorithms that we have. These are actually the most important features somehow for record linkage. So you will see dots. So when the dot is small, somehow you don't have lots of noise. So let's say that the RL problem is easy within quotes. And the bigger, the harder the problem, right? So ideally, what we would like is this dial to spot the hardness of the problem. So we would like whatever the cloud of dots is, we would like somehow the bigger dots to be located more on the right of the picture. And also what we would like somehow is to make sure that as the problem is supposed to get harder for a record linkage, it also gets harder for learning. And so we would learn model whose error is actually worse. And please notice in this case that actually we compute error on testing. We have also curves on training, but I'm going to show curves on testing in this case. So what we have done is, well, actually, that's very simple. We have just tested T and Xi as possible dial. So we have computed approximate values for T and Xi, actually bounds. But somehow we have observed, shapes in these clouds that somehow make it reasonable that the story that guides us into designing the dial actually holds, at least for those data sets. So that's kind of an interesting beginning. That's an interesting beginning because, and I'm going to converge to my conclusion. So first word of caution, our experiments were carried out on simulations of record linkage. So we haven't considered real problems. So only problems for which we were actually in charge of all parameters. We could modify all parameters. So there's some work to essentially extend this to something that's going to be more computable or more easily computable on real world settings. Yet maybe we have some good proposals for such quantities. The theory that we had somehow builds an interesting justification for this vertical partition setting in the context of machine learning. Plus, for margin immunity, it is actually observed in our experiments. So maybe it's going to give clues on how to organize this zoo of record linkage techniques for machine learning, how we can select the ones that are going to be interesting. Two last points. Our results can be extended to more losses instead of just Taylor losses, but they give more, let's say, qualitative results. Quite interestingly, actually, the bounds are better for proper losses. So a proper loss is a loss in which, the bias prediction is optimal. So for example, the logistic loss, the square loss are proper losses. Our results can be extended to classifiers more complex than just linear classifiers, but somehow the bounds that we have gets a little bit loose. So what it means is that our theory would need some serious refinement to accommodate for more complex classifiers. And that brings me to the last slide. And I thank you very much for your attention. And if you have any question, don't hesitate.
Thanks a lot, Richard, for the very nice talk on a cool topic. Do we have any questions in the audience? I can get started with one. So I guess maybe first a question related a bit to practice. So in your theory, you have so roughly speaking this result which says that the number of errors should kind of scale not too much faster compared to square root of m, which is the number of examples. I was wondering to which extent maybe in practice how difficult a requirement it is. So I was thinking somehow when m increases, maybe I mean let's say the possible number of permutations, or at least the number of possibilities, increases exponentially. Maybe you also get more similar points that maybe are more easily confusable. So can you comment a bit on that? So,
well, that's a good question. The key with record linkage is that in practice, when you have two businesses collaborating, quite often, because we actually had these cases in practice, quite often they would record some joint features. So essentially the error that you make, if they have enough, let's say, shared features, is a matter of human mistakes. So then it's essentially, let's say, the trust that you can put in the people who are supposed to record, or the devices that are supposed to record this information. That's I think one key point that could eventually circumvent your question. But otherwise, well, I suspect that there's going to actually move further in this direction. There's going to be a serious, let's say, digging into the literature, because you have so many different algorithms, and I suspect that some of them could in fact have some interesting ideas to have, if not a proof that t is going to be small, at least a reasonable a reason to believe that, you know, it could be reasonable if in practice.
Okay, yeah, your result is nice also, I guess, because it's not only about t, right? There is also these other parameters. So for example, okay, maybe you get many entries when m increases, maybe the number of mistakes increases, but maybe they get more and more accurate in a way, these mistakes, just because maybe you have more points, so you have more similar points also, and so maybe the cost of these mistakes are not so bad, although there are more. And I guess this is to some extent modeled in your analysis through this xi and rho, right?
Well, that's a good point, because actually what you have as well in record linkage is that some algorithms would actually use machine learning to do the record linkage itself. So they would be very sophisticated, and yeah, maybe that's another way to come up with some better guarantees, actually, to make the record linkage quite sophisticated and targeted precisely at machine learning afterwards.
Right. Any questions from the audience? Again, you can raise hand or ask it in the chat. Okay, if not, I have another one. Or maybe more or kind of open question, but okay, so like you said, you didn't look at generalization here in terms of results, and okay, there is obviously a lot to say already just by comparing to the just in terms of closeness to the best model in training. I was wondering whether, I mean, there seems to be even additional trade-offs, maybe in terms of generalization, maybe also in relation to this dial thing. So it's also possible that maybe adding more features also can hurt generalization to some extent, especially if there are errors. Maybe the model, yeah, maybe the trade-offs become even slightly a bit different in terms of generalization. I don't know what you what you think about that, or maybe generalization can help also. Maybe you can be far from the training solution, but good in generalization somehow.
It turns out we do have some ideas in terms of generalization, but the bounds that we have, they are not super nice. I mean, as nice as the usual ones that you would have. So there might be some, let's say, intricate game at play to actually think in terms of generalization. Yeah, that's correct. Or let's just say that we couldn't figure out.
Yeah. It seems okay, more intricate in this case. All right. I'm just looking if there are some questions, but it seems not. I have maybe a last one, maybe regarding privacy. So this is more of I guess, a curiosity, a bit orthogonal to your talk, but like you said, doing this record linkage can itself, leak some information. Either because to do the record linkage, you have to share data, or just because maybe knowing that you have points in common with another participant, maybe yet that you share a customer or something like that, this can also be maybe confidential to some extent. So I remember a bit, you guys had done, if I remember correctly, a bit of work also in this direction.
Yes. Is
it possible to basically do this in a privacy preserving way, and to which extent we can protect these things?
It is possible to converge to, let's say, an adequately private framework. And it's a little bit tricky because, for example, in this case, to link with the shared features, which of course you need to be careful about how you do that, because I mean, a birth date, a postal code, these can leak a lot of, let's say, privacy. So what we have done is we have used, these, what's the name, clicks, so cryptographic long-term keys, to in fact change the, let's say, the shared features to something that's obfuscated. But then you create noise and somehow mistakes when you do that. So then let's say the framework becomes more private, but you get more mistakes on record linkage. So we somehow made some steps into making all this private. Let's say we ended up with a reasonable, let's say, compromise with some good privacy levels, but some, let's say, machine learning guarantees at the end, or let's just say errors on testing that were not maybe as good as the one we were expecting.
Okay.
Yeah, and you had also additional, let's say, features about our problems, but this one of the shared features getting private was a very important one.
I see. Yeah, I guess the cool thing is that if you can quantify the errors due to privacy, then with this work you can turn that into errors for the classifier that you get in the end, right? So